All right. Related to the idea of a kernel is the idea of the image. Okay, and so the image of a linear transformation the image of a linear transformation T, again from R2 to R2. What I mean by the image, or this is actually what most people mean when they say the range of a function. This is just, again, all these ideas, I promised earlier I would talk about range. I just decided to put it off for a few videos. All of these ideas that we're talking about are really ideas of functions, or at least some of them are. In particular, image and range are ideas of functions. We're going to apply them to the situation of studying linear transformations. So the image of a linear transformation, I just want to write linear a little better, is going to be the set. It's going to be the set of values T of V, where V is in R2. In other words, the image of a linear transformation is the set of all your images of all the vectors V. So it's the set of images of all the vectors V in R2. And so as an example, if we were to take T, and if it were to map, if it were to be the 4, 1, 3, 1, xy, so that means that we're looking at 4x plus 3y, 4x plus y, and 3x plus y. So if that's our linear transformation, we know that, I want to say this in the best way I can explain this, and I want to just appeal to everything that we already know, because we don't need to work any harder than I don't want to work any harder than we have to. We know the following. So I want you to think about the following equivalencies. We're actually pretty soon going to add more to that equivalency theorem. But we know the following. We know that it's enough to study this matrix 4, 1, 3, 1. And we know that the nullity of this matrix, in other words, the nullity of the matrix is, so that's the dimension of the null space, is 0. That happens if and only if the null space itself, so remember that the nullity is the dimension of the null space. I guess I won't write that, but that means if and only if the null space of that matrix 4, 1, 3, 1 is 0, 0. Okay, so that's the null space. That happens if and only if the rank of our matrix 4, 1, 3, 1 is 2. And remember, the rank is the dimension, let me write that better, that's the dimension of the either row space or null column space. It's not going to matter. Let's just talk about column space. This is the dimension of the column space of 4, 1, 3, 1. Right, the rank is the dimension of the span of the columns, right? That's what I mean by column space, is the span of the columns. Okay, and we get all that from the determinant being non-zero. Okay, and so if the columns span all of R2, think about what that means in terms of linear transformations, right? If the columns span all of R2, that means that, let me actually add 1 or 2 more equivalences in here. This means that the column space of our matrix 4, 1, 3, 1 is R2, right? It's everything in R2. So that means that every vector, say A, B, every vector in R2 is in the span of the columns. So every vector in R2 can be written as a linear combination. So this can be written as a C1 4, 3 plus C2 1, 1. Okay, for some constants C1 and C2. Okay, so every vector can be written as a linear combination of those two constants. Okay, and again, what we're thinking about is if we've taken a long path to get here, but what we started thinking about was, what are the images? What kind of outputs are we going to get from this linear transformation? Do we get everything? Do we get a line? Do we get the zero vector? Do we get some other subspace? Whatever. I mean, the only subspaces of R2 are R2 lines through the origin and the origin itself, so it can't be any other subspace, but we need to think about what's going to happen. Which of those cases are we going to land in when we're talking about the image? And it turns out that since every vector in R2 can be written as a linear combination of 4, 3, and 1, 1, that's equivalent to saying that the following. So any vector AB, okay, so any vector AB can be written as, again, this linear combination of 4, 3, and 1, 1. Or, so for any vector AB, there are constants C1 and C2, where A times C1, C2 is equal to little ab. Okay, so for any vector AB, I said this correctly, but I wrote it incorrectly, so let me try it one more time. So any vector AB can be written as AB is equal to 4, 1, 3, 1 times C1, C2 for some constants C1, C2. Okay, and hence the image, which we write Im of t, so this is the image of t, is R2. Turns out the image of that linear transformation is R2.